So, fellow members, you're most welcome for today's session. And we looked at the abstract derivations, the complex assumptions made by Mr. Newton Isaac and his friend Leibniz, basically under the assumptions onto which the small derivatives in y and then x are supposed to be treated in order for us to have the real derivations, that is dy dx. And we said here we are going to be taking the first derivative, which is the coefficient or the limiting function or the limiting point of y, and that will be giving us the real definition of the derivation we are looking at. And all of this we said is referred to as the gradient at a particular point, basically the one for the curve, since we said it varies from one point to the other along the curve. And when you look at point P, is basically the one that we are going to look for is gradient. And point 2 is actually where we have gotten the second or the upper limit of the points, rather of the variables x and then y, where you have small approximations delta x and delta y added onto the original values of x and y. So it's at point 2 where we would actually say it's point 2 minus point p, that will giving you that change basically as the definition of the gradient. Now let's look at how we can use the abstract based on Mr. Newton and Mr. Leibniz for us to derive and have the solution for the given challenge at hand. You are given y, equals to x squared. So we say the small increment in y is given by delta y and small increment in x is given by delta x. And we are going to say, since we have y from our original equation and let it be equation 1, then we should add the small approximations unto the original equations whole, basically on both sides, and the respective approximations, meaning with our y, we are going to have the small increment in y giving us x plus the small increment in x. But remember, our x in this form is squared, so you need to square everything there. We move on. Our major aim is to have delta y left on the left axis, and we shall be having rewrite what we have under the right axis, that is x plus delta x, square everything, minus y. And remember, our y is given by x squared. And when we consider the bracket here, we are going to use basically the factorization method while conserving the triangular coefficients, and that is x squared plus 2x delta x plus delta x. You square everything, then minus x squared. That will give you what we have in the bracket. And so we still maintain our delta y on the left hand side, giving us our x squared, and x squared will have to cancel out, and here we shall remain with 2x delta x plus delta x squared. Now, we have to divide both sides by delta x, both sides by delta x, both sides by delta x, since we are looking for derivative of y with respect to x. And so we shall be having delta y out of delta x, giving us our 2x, the x delta x will have to cancel. Then here we shall be having the power reducing, and that will give us 2x plus delta x. Now remember, we said we want to get the limitation of the value, the least value, and that we are going to say as limbs of delta x tends to 0, then delta y delta x tend to dy dx. And that means we shall be having dy dx. Delta y delta x tends to dy dx, giving us As delta x tends to 0, then we shall be remaining with 2x, and that would give us the derivative with respect to x of y equals to x squared. Now, you have to note that what if you are given a curve y equals to x squared at points 3, 9, and you are asked to find the gradient. You're asked to find the gradient of this curve. That means you then first have to differentiate your polynomial. Then after getting the answer for the derivative, that is 2x, you then have to multiply it by the point, basically the value of x, which is a 3. For this particular case, that is that point, that will give you the gradient of the gradient of the curve at a particular point as 6. So that is how we use the abstract as we saw yesterday in our derivations, basically approximations x, delta x and delta y to solve particular challenges, especially our gradient applications. Thank you.